Nobody knows and it's late.
I click now.
Are you saying it's going to be recorded? Oh, great.
So wait for that we check the sound. Can you say something before?
Hello?
What's
Hello?
your favorite color?
Pink.
Go.
Or how do you call that? Magenta.
You sure?
Yeah.
Great. Oh, that's a nice gradient shift. I
Yeah.
like that. That's
Not
nice.
bad. All right. So then can I start? Do you think it's good?
Yes.
Great. So then I think I just start. Yeah. So this will be my presentation about DatDot, but it will actually not be much about DatDot. It will be more about Hypercore, because one issue that we're assuming or having is that although we have like a prototype of DatDot and we will refine it and make it work, if nobody's using Hypercore to build any peer-to-peer apps, then DatDot will not be very useful. So therefore, I try to present a little bit of the Hyper stack and how it works, and maybe some people find it interesting and will use it. There might be some mistakes, so if you're an expert in Hypercore or in the Hyper stack and you see any, then let me know, then I can fix those. So maybe first, what is DatDot? So DatDot will be probably a substrate-based parachain, and it offers a blockchain-based data hosting system, or maybe incentivized, but it's only for hyper data structures. So people need to put their data into hyper data structures. But what are hyper data structures? So there's a hyperstack, and it started in 2013 as DAT, and it's basically about peer-to-peer data sharing, and it has three main parts. One is called the Hyper DHT. That's basically kind of the networking and how do you discover other peers. Then there's Hypercores, which is basically the data structure, or let's say the basic core data structure on top of which all more complex data structures are built. And then there's the Hypercore protocol, which, after you discovered some peers, allows you to replicate data with those peers, a little bit like BitTorrent. Right. So how does that work in detail? Let's start with the Hyper DHT, which is the Internet of Peers, but because we're in an IPv4 world, for now we have only an overlay network. So the main thing is the Hyper DHT focuses on performance over privacy preservance, which means it's exposing basic routing information, such as the IP and the port. But it uses the noise protocol to have end-to-end encrypted connections between peers. It supports dynamic distributed hole punching as a core feature, which means it enables peers behind hardened firewalls to connect directly to each other. And also, like I mentioned, it's an overlay network. It uses Kademlia, which is like a distributed DHT, like kind of a key value store that doesn't live on a server, but in a network. Many peers participate. But if you're on a local network, it uses MDNS, which is multicast DNS, to connect to peers directly on a local network without the internet. So how does the Internet of Peers work? So for every peer, there's a few steps. So the first step is every peer generates an identity key pair. That's what you need. That's kind of your address. Then it starts and maintains connections to other peers, which means you store the discovery data, which is your IP and port, with other peers. And then which means you yourself also store that kind of data. And then you share the discovery data with other peers. So without the real IPs and ports, peers can't connect to each other. And you help peers that are behind firewalls to escape those firewalls. So the first step is, how do you generate an identity key pair? So you use the ED25519 elliptic curve cryptography to generate a key pair. And you use the Blake2B hashing algorithm, which is like a digital fingerprinting algorithm to take your IP and port and hash that, and that's your peer-to-peer address in the Hyper DHT. Yeah, and then you hash your public key of your generated key pair, and that's the topic under which other peers can look up your IP and port. Right, so how does that start and maintain connection with other peers? So in order to do that, other peers in the network will verify your peer-to-peer address, which means because your address is the hash of your IP, that means they will try to send you data and you have to respond to it. And if you can't, then they assume that you're lying about your IP address. But if your peer-to-peer address works, then this is how the process works. So these are these are all the addresses that exist on the internet. So you can imagine it as a circle, which starts with the smallest address, and then it goes like clockwise until the highest address. And the process works as follows. So a new peer joins, and he has like an IP address, and he would be in that position. And then he starts linking with other peers, and of course they verify the new peer's address, and then he maintains those links, and they're a little bit spread out. And if he doesn't connect like really to the perfect peer, then he can also ask those new peers for more peers, because all these other peers, they already know peers. And you basically just continue that process until you manage to get all the neighbor peers that are closest to your address, because you should be connected inside of that whole address space. Like every peer has an address. You should be connected to other peers that are next to you in that address space, and then have also a few distant neighbors. Right. So then once you have the data structure, which means you are a peer with an address, you are connected to other peers with an address, then any peer can start storing data in the system. And how does that work? So you take any arbitrary text and you use the hashing function again, and that creates like some little gibberish, but it's short. And it's always the same if you have the same input data. But in our case, the input data is just the IP and the port of a peer. And that's basically what we store. And it's getting stored by the peers whose address is closest to the hashed address of the data. And the data in this case is just IP and ports. And you store the data under the peer discovery key, which is the hash of the public key. So then other peers can look up the discovery data, which is IP and ports, based on the public key of peers. And another option is, because as you have seen, of course we are hashing IPs and ports, but you can use any text. So if you have any text, it could be like a whatever Astral chip as a hashtag on Twitter. So you could hash Astral chip, and then you could basically, every peer that is interested in the topic Astral chip could basically subscribe to that topic by storing, okay, my public key, I signed this message, I want it to be stored under Astral chip. So every peer that is interested in Astral chip can look up other peers that are on the same topic, which means you get a list of peers, public keys, and then you can look up IP and ports for those peers. Right, and once you got all the IPs and ports of those other peers using that system, you want to directly connect. The problem is there might be a firewall in between you and that peer. So let's say you are like in an internet cafe, or you're in a company, in a corporation behind a firewall, then that makes it hard. So you can't really directly connect. But there's a process, it's called distributed dynamic hole punching, which enables direct connections between even heavily firewalled peers. But how does that work? So how does it work? In practice, yeah, it's a challenge because firewalls, when you send a packet, they reject this packet if you use like a normal protocol, UDP, a low-level protocol. But if you send, like, because you have all these routers that are in between and firewalls, but if you send a package to the internet, then your router knows, oh, wait, there was an outgoing package. So if there's ever a response that comes back based on that same address that this package was sent to from within the company, then I'll probably let it through. So which means you have to first send a package. So first of all, we need the peer's address, which is the IP, but that's easily observable, so you will find your IP. And you need a port. So ports are usually assigned by ISPs, a little bit in secret, but they are static, which means, like, imagine those Spider-Man people. They are routers, so they are pointing to each others, and that never stops, and they have like a fixed port. The problem is, in companies, that's randomized. So there's no peer-to-peer here, because companies don't allow that, or they try to make it harder. So that's a bad situation, because if you have a known port on one side, and let's say the IPs are known, because you can look them up easily, but the other side has a random port, then how will you connect? That's pretty bad. Yeah, so that's tough. But it gets worse. So because we are in the IPv4 address internet, and we ran out of IP addresses many times over, you have not just one router, you have many routers. So basically, the router that you have, maybe at home or in the company, there's like also your ISP has routers, and there might be multiple levels of those routers, and then you come only to the internet. And on each of those routers, there can be random ports and all kinds of things, so it makes it not easier. So yeah, but is it hopeless? Never. We can maybe punch through this with some tricks. And we're using hole punching. But what is hole punching? So ideally, you should be able to connect to peers directly, but and we can try to do that with the technique that is called Udp Hole Punching, and that's also commonly used. And how does that work? Well, how do the basics work? So if A, like that's one peer, sends a message to B, then you first send that message, and your router, it will pass through your router, and the router will tell you that it allows a reply from the receiver of that message, or the specified receiver of that message. But if the message arrives on the other side at the receiver, their router, of course, will just not let the message through, because there was never a request that asked for any message from the peer A. So the message will just be dropped. On the other hand, if B sends a message to A after this first process already happened, then of course their router will first let the message out to the internet, and which means the router will also let a reply through. And on the other side, the router, because peer A already sent a message to peer B, and now this message is from peer B, that router thinks, oh wait, I may be expecting a response, so I'll let that through. And now that this message arrives at peer A, now there's basically a full normal connection. Now both peers A and B can send as many messages as they want, because both of their router kind of think that there's a communication ongoing, and those can now go through. So, but there are requirements, right? So the requirements are, it only works if both of them know their IP and port, and as we saw, there are some ports that are random, so I need to know that before I can even start sending messages. And second, it has to happen at the same time, so A and B need to kind of know that they're supposed to send messages, because if A sends a message and it can't get through to B, how does B know that we can now, that he is supposed to send a message? All right, so how do we learn about ports? So assume that one peer already, the IP and port is publicly known, but the other one is on a random network. So the IPs and ports of the initial bootstrap nodes in the network that when you for the first time want to join, they are known. So that's a good thing. And also, you can discover more peers. Maybe you already participated in a network, so you can save some peers that you already discovered in the past, and they can be saved. And also future peers that you might discover once you're connected, you can save them. So therefore, you don't need to ever talk to the bootstrap nodes again. That's just like a one-time process. Right, and those peers that you connect to initially, they can help guessing your ports, because you already know their port and IP you connect, but now they can try to figure out your port if you want to connect to other peers. So if we start guessing, so there are only 0 to 65,536 available ports. That's just how it is. You can't select any ports on computers that are lower or higher. It's actually even lower because there are some ports in between 0 and maybe 1,000 or the few ones that are reserved. So you should probably use anyway higher ports. And it would work like this. So let's say the first peer has a known port. Both have known IPs. The other one has a random port. And this second peer with the random port, he sent a message, which means he allows to reply. He allows a reply. And now we have to figure out the random port. Therefore, peer A can send a message like to port Y. And if by any chance X and Y are the same, it would work. Otherwise, it wouldn't. So we just have to guess, and there's a lot of possible guesses. So that could take some time. Can we improve that? So this is luckily similar to the birthday paradox problem, which means if you do some little bit of math, if instead of opening just one port, we open just many in parallel, like 256. That's what we want to try. Which means if we are sending out a lot of messages to the same peer on the other side, but then we get basically a lot of different ports that we open. So on that side, that will be kind of the same router, but it's like different ports that are open. And then on the other side, yeah. Oh, wait, maybe I have to zoom out a little bit. Oh, maybe that's too much. I don't know, actually. Oh, no, that's fine. Okay. It's hardly readable now. But right, so basically it just says like those ports are now open. The messages here, they kind of disappear a little bit because, yeah, they can't arrive on the other side. But now if we start guessing, we can send messages to many, to many ports in parallel. We just try them. And if we by any chance like have a match, then the connection is established because from now on we can just use that port, and because that message will arrive to peer B, he knows where it came from, and a message channel is established. So how many guesses do we need? So there's 65,536 options and 256 possible correct guesses. So that's a little bit of factorial in math. But basically the math will say that 174 guesses gives a 50% success chance, and 2048 random guesses give 99.9% probability to establish a connection. That's not too bad, and it just means in practice it's actually fast enough. And we also only need this to establish an initial connection, because from then on we can communicate directly, and that's fast. So that's maybe in the beginning, depends on the situation, can take all between a fraction of a second and a few seconds, maybe sometimes more, but it should kind of work. So, but isn't that an attack? So if we send so many packages to the other side, maybe the firewall will block us because there's too many messages coming in. That's not good. How can you make it not an attack? So packets only need to exit our firewall to open basically the firewall to the response from the outside, but they don't have to arrive on the other side. So we can just set like a very low time to live, so those packages can basically disappear immediately, which means if we're blasting like a lot of packages, they can just basically, they allow the connection, but they don't have to arrive on the other side. Do I have here a fourth picture? I'm not sure. No, good. Great, so that works, but how do we make all of this decentralized? So distributed peer-to-peer hole punching. So the traditional hole punching requires like a centralized server, but we don't want that. Maybe we need a few bootstrap nodes, but at least let's get rid of using always the same centralized server. So in HyperDHT, we can basically it's a feature built in, so you don't only get this key value store where you can store your connection information like IPs and ports and or subscribe to topics. Every node is also automatically participating in a decentralized hole punching procedure. So if there's, let's see, that's the second requirement, right? The first one, we need to know the ports, and we figured out how we can learn them. And the second one is the timing. Let's see. So if we have like one node to this, we discover a new peer because the bootstrap node told us, oh no. So basically, we're getting a little bit of assistance from not actually one node, but multiple nodes in the decentralized hash table that all nodes on the network participate in to punch through the routers. And then we don't have to do it alone. And they can also inform the peers when they should do it, at what time. And it's also good because messages come then from very many different peers, instead of always from the same ones, which makes it more likely that they maybe get blocked or by firewalls or some other problems appear. All right, so and that's basically the, let's see, that's basically HyperDHT. So it helps us to, so it's the whole thing is the hyperstack. So we have the HyperDHT, which is basically the networking part, which comes with the hole punching and storing of IP addresses in this distributed hash table. And it's also storing lists of peers based on topics that they subscribe to. And when you look them up, the peers, and get their IP addresses, it also helps with hole punching to establish connections. So you get now peer-to-peer connections. But now we have another part to this system, and that's about data structures. So maybe when you build apps, you need databases, all kinds of databases. Maybe just a key value store, but maybe also more complex databases. And in the end, the third one is the Hypercore protocol, which helps us to replicate those hypercores or any database or data structure built on top of hypercores with other peers that we are connected to. And we find those peers using the DHT to look up their IPs and ports based on their public keys, or look up lists of many peers based on some topics like Astral Chip as a hashtag. Right, so how do hypercores work? So basically, hypercores are blockchain-like append-only logs. So let's see, what does that mean? Did I put a link here? Basically, you just have a block of data, and then you create another block of data, and then you create another block of data, and you just do this until the end of time. So it's pretty simple. Those blocks can be Merkleized, which means, what does that mean? So you're using this hashing algorithm. For Merkleization, you need a hashing algorithm, and what it means, it looks like this. So if you have a bunch of blocks, then if you want to Merkleize them, it looks like this. You take this data, make a fingerprint, and you do that for every block, and then you take two of those fingerprints, put them together, and make another one, and you do this as long until you get like a final fingerprint, like the root fingerprint. Right, and if somebody requests a block, you can hash that block, and if they also provided you with those hashes here, you can take those, hash them together, and see if you get the same root hash. And if this root hash that you calculated is the same as the initial one that you had, then the data is not been tampered with. All right, what's the next step? So there's another thing, and that's we sign with our private key. The person who creates the hypercore has a key pair, and they're signing the Merkle mountain range root with that key. So that looks very similar. But when they sign the root key, it's basically you're signing this root key. And then if you append data, you create more hashes, so the data changes a little bit, or is extended basically, this Merkleized, this Merkle mountain range. And you always sign the new root. So you always get new roots, but when you sign them, then whenever there's a single data chunk that you want to download from this entire data set, or multiple, you can use those to calculate the root hash, and then you compare it if that hash matches the signature that was created, the digital signature. Right. So basically, our blockchain has like a proof of private key possession consensus. So as long as any data from the blockchain is downloaded, you can use the public key to verify the signature of the Merkle root, and the Merkle root proves all the cryptographically that all the data chunks that you got belong to this data set, to this blockchain. Then that's consensus that. Hmm? Oh no! Did it just break? All right. Okay. So yeah, so basically in a blockchain you have a consensus mechanism, and in this case it's consensus that every block in that chain, when you build the Merkle tree over those data blocks and you get the Merkle root, then that Merkle root hash or fingerprint needs to match the signature that was created. And basically what that allows is that you don't have to download the entire data set. You can literally just download a few blocks from the whole data set, but still verify that they belong to the same blockchain. And that's pretty cool, because if there's a lot of data in the blockchain, you don't want to download the entire data set if you're just interested in like a small piece of data. And yeah, because there's a key pair involved, the public key happens to be the address under which you can store. Basically, you use the address or the hash of the public key, is the discovery key. You use that as a topic in the DHT. So if you basically, you can subscribe to a random topic like the hashtag astralship, but you can also use the hash of the public key and basically publish that you have this data set, and anybody who is interested in the data set, they can find all the peers who are subscribed to the same topic, which is the hash of the public key of that data set. And once they find peers to replicate the data from, they will already have the public key of the data set, because that's how they found those peers in the first place, by looking up peers on the network that are interested in that public key data set. Which means if you now get all these chunks of data, if you request it and you receive it, you can build again the Merkle tree by hashing all the individual chunks and then verifying the signature with the piece of data that you started out with, which is the public key that you need to verify the signature, which you got because it's also the address of the data set. Right, new peers need to, oh right, and there's one catch. So why is the hash of the public key the address? Because that means that the public key itself is also some sort of a password or something that you need to know, and you have to prove it to other peers in the network that have the data set, that you know the public key. And if you don't know, they will not share any data with you. So just looking up peers, you can do that, but you still need to prove to them that they have a public key, which means it's not possible to just sit on the network and scan and ask arbitrary nodes for certain data sets, because you have to know the public key, and those are not shared by default. Those are maybe shared offline or in any other different ways. If you publish a public key, then it's a public data set, then anybody can, of course, look it up. But yeah, that's just how it is. And what's the last step? Oh yeah, the Hypercore protocol. So once you have a lot of connections and you want to synchronize data, it basically enables the peer-to-peer data sharing, because the hypercores are the data structures and the other one is how you find peers. But once you are connected to peers in a direct way and you have the data structures, you need a way to replicate the data. So basically, yeah, when you discovered the relevant peers on the HyperDHT, you end up with a reliable streaming connection, which is based on UTP, which is a little bit like TCP, but it's building on top of UDP protocol directly. Oh yeah, all right, I wrote that here. Yeah, the Hypercore protocol is peer-to-peer data replication mechanism to replicate those logs. And it's a little bit inspired by BitTorrent. So basically, it works as the more peers you have for a given data set, the faster you can and more reliable you can replicate it. Oh no. So let me zoom in a little bit. So if you are maybe, so this BitTorrent tracker, that's replaced by the DHT, by the network. So there's not a single server anymore that stores any information. But once all the peers found themselves and you, as a peer, you basically used the decentralized network to look up the peers instead of a single computer, you can now, from all these peers, all of them have a little bit of data, you can download in parallel from all of them to get the data a little bit faster. And if any peer goes offline, doesn't matter, there's more peers available. And it looks just like this. If you use it on the terminal, it just gives you a little bit of peer connections and shows you how fast your upload and download speed works. Oh, how do I close that? No, I want to go back. Yeah, and Hypercore protocol messages, just to get like a little impression how that works. Every peer remembers the chunks that they want or have. Basically, they say to other peers something like, I want to download this chunk, please tell me if you have it. And then, of course, having chunks means you would say, I know you want this chunk, and I will send it if you ask for it. The reason that's like this is maybe if you want a lot of chunks, you can, do you have any chunks or blocks? Basically, we are talking about a blockchain between the range of 100 and 10,000. And then you find first peers that have, that say, yes, I have those ranges. And then you can basically ask those specific peers, hey, can you give me this and this and this block? To kind of minimize a little bit how many messages are getting sent. Yeah, if you only, as with peer download, delete. Yeah, so basically the core message types is more like if you write like a letter and send this as a message, you would like in the subject you write this is a want message or an unwant or have and unhave. And it means just more like I want this block, and then somebody can reply with a have message that says I have those, and then you can also cancel those requests. And these are not all the types of messages. It's basically goes a little bit further. There's in total like around 10 message types. So once upon a time, that was the list. It's a little bit outdated, but it's basically, so you basically can talk about a feed, so that there is a hypercore, and that hypercore references another hypercore, gets a metadata. You can have the have message and unhave, which means I have the chunk, but if you then delete it, you can say, oh, I don't have it anymore. You can say that to the network. You can say that you want certain chunks, or that you don't, that you're not interested anymore. And when once you decided, all right, these peers seem to have those chunks that they want, you can actually request them for real, and they send you the actual data of that you want, not just the number of the chunk, because in a blockchain you always have blocks, and the number only ever increases. And then they give you the type of data to send you actually the data back. Or if they didn't do that yet, you can also cancel your request, like, oh no, I changed my mind, I don't want it anymore. And then a special extra message is like extensions, so you can define custom message types if you want to, but they're not strictly necessary for just the Hypercore protocol. And that's like a little conversation, how it would look like on a chat or in a messenger. So basically like a download like is a want and have messages, and then request messages, and then here they send the actual data. And that's it.
Oh, great.
Questions?
So is it?
Oh yeah, sure.
Hello. I have a question. So with the request for various chunks, obviously this depends upon the data set, but you just had an example there at the end of people having a little chat asking for data chunks, and so that is people enacting those, and it's not just protocol of the system to get the complete set of data. Like it is within this specific thing, it is people asking within a set of data for. Obviously you can use it for different.
So that's actually just like meant to be computers talking like in an automated fashion, but you could do it like this. You could literally write like a little chat program with a bot where you type in those certain messages and then trigger the things. But usually people would build like an app, and so the thing is an append-only log or like a blockchain is like a very primitive data structure. It's almost useless. But the cool thing is there's an easy way to build basically any kind of data structure on top of them. And the way it works is like if you imagine, for example, a file system, you would create a folder, then you would create a file inside, you would delete the file. But these are like commands, like create folder with a name. And if you save all these commands in the order that you do it as blocks, then you get like a log of all the operations that you ever did. So if you then, and that's basically such a hypercore, which you can replicate. And then once you replicated it, and you know that this hypercore, all the blocks, they basically contain the commands that were meant for a file system, you can just replay them. And therefore, it creates you the same file system structure. Or if it's another type of data structure, like a key value store or any other database, is actually basically the same. And of course, you can be smart about it and do it a little bit more sophisticated, but in the basic case, you could just literally record all the interaction with the database, one command at a time, and just put them into blocks. And then anybody can replicate them and recreate the exact state of the database. One thing to have in mind is, of course, that only the author has the private key, so therefore they're the only ones who can create a new command to change the database, because then once they did that, they built the whole Merkle tree, and the Merkle root can only be signed by the author who has the private key. So nobody else, none of all these other BitTorrent style peers can create a new message that would have a valid signature. Only the original author can, but from then on, anybody who joins that blockchain network, my personal blockchain basically, one of my personal blockchains, they can replicate the blockchain. They can use the public key to verify that the block was created by a proof of possession of private key. I can prove that with my public key and verify it. And therefore, I know that this data set, this data chunk, the new one, the update, came from the same author, and everything is fine. And so therefore, I can have many, many blockchains, and others can have many, many blockchains to store our personal data, and I'm the only author, and others, or anybody who's interested, can join my blockchain network and download my blockchain and replicate the data that is stored in there, which could be, of course, representing a file system or any other database. And usually, I wouldn't even do that. Probably, I would just use an app, like let's say a chat app or a video live streaming app or any other kind of app, maybe a game. And then the game, when I started, or the chat when I started and use it as a user, it would just, every time I'm writing a message in the chat, it would probably, in the background, append it to this hypercore. Or if I'm using the game, behind the scenes, by every time I do a move in the game, it would store that in the database, which is another command to change the database, which would be stored in that hypercore log as another command. And then all the other peers that join me in the chat or in the game as a multiplayer game, they would replicate all these hypercores and then replay the same commands. First, they of course verify that it actually came from me, and then they build up the same state, and their app, their chat or game can display the same state. So that's kind of the idea. Yeah. Right. So, and that's why, of course, I hope that many people like it, so that this all can be done peer-to-peer. And it's also ready, and there are some example apps out there that are using it. We had even other speakers presenting some of them. One is called Keat, which is like a peer-to-peer alternative that's using exactly that stuff to create an alternative to Zoom for live video conferencing. Then there is Cabal.chat, which is like a IRC-style chat app or Discord-style chat. I mean, it's not as advanced as Discord, but it works. And we had also somebody presenting us Share, which is like a peer-to-peer more radio app where you can basically go live and I don't know, play music or talk or whatever you want to do. It's audio only, and others can basically join in and listen to you, but it's also all peer-to-peer. And more apps can be built.
You know, my understanding is limited, but how is it? So within, you say you have this specific Hypercore blockchain package. How then is it? What is the communication that is then developed? Like, how is the blockchain further advanced by other people that don't have the private key?
Oh, right. So it actually is not. So I'm the only one who can advance my own blockchain, but others can create their own blockchain. So for example, let's say in the chat program, once many peers join, like we all use the DHT network to discover each other, like every participant in one chat room would create their own blockchain, maybe just for that chat room, and then they would just subscribe to the blockchains of every other chat participant. Okay. So there's basically at least as many blockchains in the game as there are participants in the chat. There are ways to make it a bit more efficient, but I mean that's the basic principle. And then the chat program, like the app that you're using, would basically join on the DHT network all these different blockchain networks, download all the chunks from everyone, and then based on how, for example, one message in one blockchain references a message on a different blockchain, or maybe you can use timestamps or different ways, you can then basically replay and show them in the chat program for everyone in the same order. Maybe we can use the stuff that Mikola presented earlier.
So say that then one of these players, one of these blockchains then is unavailable within the network, then that just shows like a blank space within the communication log. Like say if they're being used as a chat, for example.
So yes, and that's kind of pointing to the problem that can happen. So if there's like let's say a live video stream, everyone is actually online. If it's a live chat, then also everyone is online. But if it's like, let's say, a chat and somebody writes a message and I'm maybe asleep because I'm in a different time zone and the next day I come online and I want to read stuff, if that other person is not online, I can't even get their data. So this is actually an issue, and that's exactly the reason why we're actually working on DatDot. So having like a blockchain that is a incentivized hosting system, so you can basically pay peers, pay anyone that participates in the DatDot blockchain, which is not Hypercore based, but is substrate based. So basically the basic principle is if you run a DatDot node and you have empty disk space on your phone or on your desktop computer, or if you're a professional and you have a whole server farm, that's great too. You can offer that empty disk space to the network, and also anyone who's using a peer-to-peer app, that's what we're working on at the moment, they can take their Hypercore addresses and define chunk ranges and have like a bunch of options to define how and where they want to have and from when to when they want their data to be seeded by other peers. and then they tell that to the blockchain, and then basically the blockchain matches people who want their data to be hosted and those who have empty disk space. And then those who have empty disk space, they get like paid in a token. And the others have then basically those other peers that are not themselves that keep their data online while they are offline. So if I basically pay on the DatDot blockchain and say I want my chat messages to be available at night because my computer will be shut down and I sleep, then I'll pay a little bit and then they basically join and replicate all these chat messages from me and keep it online while I sleep. And then maybe in the morning I stop it because now my computer is online, so I don't need it anymore. Or maybe I can also during the day use my computer and my empty disk space to run DatDot in the background to rent out my disk space, which earns me some tokens that I can use at night when I sleep, so others can store my host my data then.
I would do it the other way around.
All right.
When I sleep, I don't use my computer.
Oh, so fair enough, yeah. So yeah, you can also be smart about it and see what would be the best way of doing that.
This is why you have the hat.
Right. This hat, yeah, maybe. Yeah. Are there any other questions or? So yeah, maybe we have, I think, one talk about DatDot that goes more in depth from last year. Maybe I can also make another one. But basically the last talk is still more or less tells the entire story. But I think we didn't yet share much about the details about Hypercore. And we soon or very soon need some people to start playing around with it and building some Hypercore-based apps so that it makes sense to use DatDot.
So if somebody is interested in where, in which stage of development is currently DatDot, can you just share a little bit?
So we had like when we started with DatDot like 3 major milestones, and we plan to do them in 3 months. But we so far managed to complete 2 milestones. But instead of, it took us 2 years instead of 3 months. And we are now almost like in the 3rd year, but we are also close to the 3rd milestone. So instead of 3 months, we should have probably estimated 3 years, but okay. And I think when it comes to the blockchain part, more or less, that's more or less pretty much feature complete. And that's what also was the work that we did in the first 2 milestones. Our blockchain, or the definition of the blockchain, is basically written as a server. So the server is written in a way that it behaves like a blockchain, which means any transaction or extrinsic that is submitted to it, they end up in a queue, and every 6 seconds or whatever the block time is, they get processed. So the idea is, or what we found out in the beginning is, that iterating between JavaScript, because all the Hypercore stuff is implemented in JavaScript, and Rust, and compiling and going back and forth, that takes a lot of time. So we just started implementing the entire logic in JavaScript and simulated basically the chain. But we tried to focus on readability so that we can then translate the entire logic and put it into Substrate. And that's kind of where we are at the moment. So we are looking for somebody who would help us to implement the whole thing in Rust. We also found somebody who is interested, and we also reached out to the Builders program, but we're currently waiting for their response. Otherwise, the part that we also need is a little data wallet, or some place where people can actually interact with the chain, because the idea is that we want people to be able, we started recording videos to teach people how to build peer-to-peer apps. We're kind of halfway through, and we'll probably finish the rest in the next weeks or maybe even month on the site. But in order for people to follow those tutorials and then start building peer-to-peer apps, and also for us to build our data wallet, which in our initial plan, which was supposed to only be executed in 3 months, that included a little UI or like a wallet with a UI that allows people to offer their disk space, basically fill out a form. This is how much disk space I have. This is from when to when I want to rent it out, so that they can actually make that request. And on the other hand, also that people can, when they have some Hypercore-based data, that helps them to select the addresses in the chunk ranges, because if you manually have to go and say, that's my Hypercore address and I want to replicate chunk 75 to 10,360, that's kind of tough, because ideally you would want to have, I want to just share, I want to replicate the data that's in that chat or in that file and folder, and it's much easier if you have like a little interface that helps you. So, and lastly, we of course want people to be able to use those apps in the browser. So we're building a little bridge, so people, when they download DatDot and use it, they can run the blockchain node, and they can also open web pages or build web pages that make use of it. So instead of storing data in the server or in the cloud or in any traditional infrastructure, they can just have a static web page, like a single HTML file, which then interacts with the hypernetwork in somewhat similar ways to how normal web pages interact with blockchains, by using a wallet like MetaMask or other wallets. But in this case, it's not just like tiny transaction data that costs maybe even a lot, but it can be like gigabytes and gigabytes of data, and it's basically free. There's no token involved until you come to the part where you actually want to pay to the blockchain to have other peers that store your data. But that's still much cheaper than regular blockchain transactions. Yeah. Does that make sense? Okay, cool. So, right. Yeah, thank you. If there's maybe one more thing. So if you're interested, like on the Wizard Amigos Discord, but we have, I think, somewhere a link to the DatDot Discord. So we have a separate Discord server for DatDot. In case you want to learn more, there's also the webpage DatDot.org, which, I mean, shares some of the documentation and the ideas, but then we have also DatDot.org on GitHub and a Twitter account. But on GitHub, basically, there you can find all the details and the implementation, and also all the open issues that we're still working on. And yeah, on the Discord server or on GitHub, you can ask for more questions, and we can answer.